Hi, so today we're going to look at a project of mine called LIBDSM. So what is LIBDSM? Well, it's essentially a distributed shared memory library in the form of a software library. So that's essentially written here in the sort of subtitle for the project. It's for Linux. Any sort of distribution of Linux can or should run this, and it's available for free on GitHub. So what are distributed shared memory systems? Well, according to Wikipedia, it's a form of memory architecture where physically separate memories can be addressed as one logically shared address space. So in perhaps my own words, this means that if you're running a computer with shared memory, the computer provides in some capacity addressable memory such that each process can access the same memory despite being in physically separate places, perhaps. So typically, shared memory is a hardware feature, and this means that on multiprocessor systems, the hardware provides the shared memory for you, and so this means that a lot of the solutions for shared memory are sort of tied to hardware architectures. But as you can see, that's not the only way to do it. It can be implemented in an operating system or as a programming library and can be thought of as extensions to the underlying virtual memory architecture. And this is where I come in with a software-based solution, which is essentially a programming library. Now, when you normally do shared memory, if you implement it in an operating system or as its own compiler, you sort of commit yourself to a rather large project, because on an operating system level, implementing shared memory usually means making changes that require you maintain your own version of the operating system. And this becomes very difficult on operating systems where you essentially have to keep up with yearly releases and make sure your product is up to date. And it can be oftentimes unsustainable, and these sort of projects disappear. Doing it as a compiler is more easy, but again, you have to keep up with the evolutions in the programming language, and if not, you can get stuck, in older versions of the language, and it's a problem. So the most portable or maintainable way to do it is as a programming library, and that's what I'm talking about today. So let's go back to LibDSM. LibDSM is essentially a static library, and so when you install it, it will go into user local lib for your local libraries, and it will put some headers in user local include, and then you can use it in your own programs. It doesn't say so here on the README, but LibDSM essentially is written to be used in C programs, and it's written in C itself. So if you're developing in C, this is essentially a great tool if you quickly need some sort of shared memory system. I suppose it's also possible to then use it in C++ or Objective-C, but right now I've only developed it to be easily used with C. So let's take a look at how you can install it and how you can run it. The first thing is that you're going to need to install the dependency. So there's only one, and that's that you have Intel Z. So what is Intel Z? Intel Z is a disassembler, or as they put it, a encoder-decoder software library. So why I need this is because Intel Z can be used to disassemble compiled machine code that has been compiled to machine code from x86 instructions. So I need that for several inner workings of my project, where I have to discover what modifications you've made to memory, and one of the ways I do that is by injecting an instruction somewhere, but that's kind of irrelevant, so we'll go back to how you can install this. So the first thing you want to do is clone the project, so we'll do git clone https github.com/micrified. It's my username on GitHub /libdsm, and we'll put it in libdsm. So it's cloning it right now. We're going to get a lot of crap outputted on the screen. There we go. So once that's done, we can try and install it. So cd into libdsm, and you see the contents of the folder. We've got examples, the header file include. We've got the source file, we've got tests, and then of course a license and a README and all that. So let's do make install. Or I'm sorry, make first. You want to make the project before you install it. And once I do ls again, we'll see, you can see that libdsm.a, the static library or archive file, has been created. So then we can do make install and copy these files into user local bin, and then the headers into include/dsm. Alright, so we've installed it. Now how do we use it? So in order to make it useful, I've created and included some examples of how you can use the shared memory system. So let's take a look at both the interface and one of the simpler examples. So cd into examples, and we'll cd to template. The template is essentially the hello world program. So libdsm examples template template.c. So what do we have here? Well, it's easiest to explain what we have if we're referencing the interface. So let's look at the interface. Just give me a moment. Whoops. I don't know what I just did. I'm not used to using Acme. Okay, looks like we've got everything here. Let's just pop that up. All right. So the interface provides you with a selection of different functions you can use. The most important is the initializer and the destructor, DSM init and DSM exit. These start and stop the shared memory system. The rest are mostly functions, directives, features that you might find useful. For instance, get GID, global identifier. This is great if you're working with a system where you're running across several different nodes and you want to know what's the identifier globally of my process. But we'll get back to that later. Let's look at the example. So here I declare a couple of variables. We've got session ID, which is a string, and I've named it template. We've got the number of local processes we want to run, lproc, the number of total we want to run, tproc, the size of the shared memory space, which I have here as the size of a hardware memory page, and then we have a pointer to the shared memory. So in this system, you're going to be returned a pointer to the shared memory space that is of the size you specify in the initializer. As you can see, we have passed map size in as a parameter. And that will be your shared memory space to use between processes. I don't automatically share the process memory space myself in the sense that, you know, it magically becomes shared. That doesn't happen. You have to use the memory that is in this map. And it's essentially a mapped file or object in memory. So the initializer just wants your session ID, the number of local processes and total processes, and the map size. And this is essentially the easy initializer. There's a more complicated one called DSM init 2. And that will start your shared memory system, and you'll be returned a pointer which points to your shared map. The initializer also does forking. So here we've specified 4 processes in lproc. So, or lproc has the value 4, which means that this initializer will fork 3 other processes in addition to this main program that is, or main process that called it. So that will result in a total of 4 processes, and then they will all print hello world, and then at DSM exit, the child processes will exit, and the parent process will wait for them, and then finish. So diverge at the initializer, converge at the destructor. So let's, actually run this instead of just fiff-faffing about. My bad, just want to move this up. Okay. I'm sorry, we don't have a make file. So here we'll demonstrate how to compile it. We'll use GCC, and I'm going to name this template, and we'll specify template.c. Now, you're going to have to link this with a set of libraries in order for it to work. I've handily named them up here in the example. So dash LDSM dash LP thread dash LRT and dash LZ, and we're done. We've compiled it. Template is available and ready to run. However, before you can execute this, you're going to want to run the system or the shared memory daemon, and that's a very important part of this system. So shared memory daemon, let's go to, well, we don't need to go anywhere. It's already been installed. All you have to do is write our LIBDSM daemon, and it should say it's ready and waiting. So as you can see, the daemon's ready at localhost on port 4200. You don't need to mess with this. The system automatically knows where to contact the daemon. And here we'll execute template. Let me give us some space first because we want to okay. So things are a bit wacky, but let's look at the output. Each process, 0, 1, 2, and 3, although he's right here, printed their hello world statement. So this demonstrates how the example forked several processes. They each printed hello world using their global identifier, and then they converged and we exit the program. So this doesn't directly show the shared memory in use. It shows the global identifier system in use, really. But it also shows how the system can automatically produce forks and converge after. But I'm going to go to a more complex example now because this is really just a hello world program. So let's get rid of this and let's go to the primes program, which I think is a much more instructive example. CD back and go to primes. All right, so what is primes? Let's take a look at primes. I'm sorry, I need to access files through primes. So that's examples, primes. Okay. So primes computes the number of primes between 0 and some upper limit. So we've got an isPrime function, which returns non-zero if the number given the unsigned integer is prime. Otherwise, it returns 0. Yeah, returns 0 if the natural number is not prime. We've got the main loop, which scans in the arguments and then runs several rounds. So the rounds are just for testing, so we can kind of ignore that. This is the meat of the function here. So what are we going to do? We're going to start a timer. We're going to initialize the shared system, so all forks diverge. We get our rank. We compute a subset of the integers between 0 and our upper limit based on our rank, and then we add to a shared sum. Then we wait for everyone to finish, stop the timer, copy the result out of shared memory, exit, all forks converge, and then the remaining parent process prints the number of primes. So let's run that. Make, and we'll do, whoops, don't know what I've done there, /DSM primes. All right, so that tells me what the input needs to be. We want 4 processes to compute 50 million primes once, one round. So let's wait. That should only take about 5 seconds. There we go. So as you can see, the number of primes between 0 and 50 million is, what's this? 300,000, 1,134. So that was done in 5.025 seconds, and that's not really, doesn't really give you any reference, but it will if we run this sequentially. So let's run sequential primes. This is a sequential version. We want to compute starting from 0 up to 2 million. And now it's working. So let's see how fast the sequential version is. It should be slower than the parallelized version, and that would be a demonstration of how you can use shared memory effectively. All right, so we're waiting. All right, 17 seconds. So yeah, this is one example, perhaps the best example, of where shared memory is useful, and that is when you have a small number of variables that you need to share between different processes. So what I've done here is I've said sum is going to be a pointer to integers, and it points to the shared memory space that I've just allocated. So I've allocated a whole page for essentially an integer, which is 4 bytes only, but that's kind of you have to allocate at least one page, so that's just going to happen. But the use of the shared memory space isn't too important here. It's the fact that we've allocated a shared sum. We each take turns adding our piece of work to the shared sum, our number of primes between whatever segment we were computing. It's not really a segment. They're each sort of jumping over each other to compute their own primes, but we each add to the shared sum. That's the point, and then we stop, and then the master or parent process prints the result. So perhaps some things stand out to you here. For instance, if the memory is shared, why can't you all just add to it, all processes? Why do you need this guard? Well, that's an important question, or a good question, and it's one that I didn't run into until later in the development of the system. And one of the problems with implementing this as a library, and this may apply to even actual shared memory systems, is that the registers of the process itself can act as a cache. So what happens if two processes want to add to the shared sum at once? So the sum starts out as 0. Just by the way, whenever you allocate shared memory, my system zeroes it before you get it, so it's always nulled. But suppose one process wants to add 10, the other wants to add 15. If this were to happen in an ideal system, you would get a result of 25, even though they both tried to add it once. What happens in my system is that one process will, try to add 15. It will request access to write 15 to the shared memory. It's going to be adding 0 with 15. The previous value is 0. The value it's adding is 15. And the result should be 15 when it's done. The second process, which requests basically at the same time, requests write access, and he wants to write 10. But the value at the time is 0. So both of them load 0 into their registers. One of them, the one adding 15, wins the race. So he adds 15. And the value 15 is synchronized globally to all processes. However, the second process then gets authority to write, and what happens then is that it adds 0 to 10 and overwrites the 15. It does not add 10 and 15, getting 25. And the reason that happens is because 0 was stored in the register, the process register. So it's essentially a miniature cache, and you lose information because instead of refetching the value from the memory address, which has since changed, it just uses the value in the register, which is essentially 0. And that's just a flaw. So whenever you're adding to these types of things, you're going to want to use a semaphore, which I provide in my system. So DSM wait semaphore essentially says wait on the semaphore identified by this string. I've called it the sum guard. So you wait, which means one process at a time can perform the instructions between the wait and the post. One process will update it and then release the semaphore. Another process will gain access, and then it will use the updated value, and that's just how things are. The barrier directive tells everyone to catch up to the same point in execution. Why do I have a barrier here? Well, the reason is that we don't want the parent process to do his work and then just print the half of the sum out because he finished. Everyone needs to finish adding to the sum before we can proceed. So barriers, even though this is a shared memory system and you do not want to see directives that you would find in message passing libraries and things like that, you have to have some just for the programs to make any sense. And once that's done, the rest is fairly simple. Oh yes, here you see that I'm copying the value of sum to result, which is a local variable. Yes, so this will be on the stack. Why am I doing that? Well, the reason I'm doing that is that I called the destructor here. So the moment the destructor is called sum, which was a pointer to the shared memory space, it becomes garbage. It's pointing to essentially an area in process memory that is no longer valid. The exit function call removes the shared memory space from the process. So this is going to be, this access here becomes a segmentation fault. You're accessing memory you don't have the authority to. So you always want to make sure to copy values out of shared memory before you terminate or call the destructor. And that's it. So what we've seen here are two examples, one pretty trivial, the hello world, another actually useful, of how you can use shared memory. So back to the project. If you want to use this, you're going to have to basically ensure that you're running it on on a system that is using Intel's x86-64 architecture, so 64-bit instruction set architecture. It's only for Linux right now. I've tried to support Mac OS, but the problem with supporting Mac OS is that it doesn't exactly work well on systems like El Capitan, at least so far, and I haven't tested it on High Sierra or Mojave or anything else, but I don't believe it would work any better. You also have to have Intel Z, and you have to make sure that the hardware memory space is, or the memory hardware between the systems you're using is identical, because it's going to be copying raw memory around, and you don't want to have memory from one system being copied to another where it doesn't make any sense. And that's pretty much it. So if you want to contribute to the project, it's fairly easy to do. You just basically can fork it or post issues or do anything like that. It's available here on GitHub under an Apache 2 license. And I suppose that's it. So I hope this video was instructive in some form, and thanks for listening.